Okay, I'm pretty sure it's recording now. If it's not recording now, I will have some trouble later. Anyway, hi, thanks for coming, everyone. This lecture, as I said, is for the data science team in Italy, mostly. So before I start, let me just say, please do interrupt me if I am talking too fast for our non-native English-speaking colleagues. I tend to do that when I get carried away, so just please interrupt me if I'm talking fast. I also want to note that there are additional slides that aren't going to be shown here to provide extra context and explanation. So if you're interested in this stuff, look over the slideshow, and a lot of things I say that aren't on the slides are there on these intermediary ones. But yes, hi, I am Evan Miller, Senior Data Scientist, and today I'm going to be talking about do calculus. This is a Bayesian theory for causal inference. So we are talking about a statistical framework for defining causality. I just want to be clear that by causality, I don't mean anything abstract or complex. I just mean the simple philosophical concept that sometimes things happen for reasons. So this is just a brief overview of what I'm going to be talking about here. I'm going to go over some background. I'm going to go over what exactly we're talking about causality. I'm going to go over some common examples from statistics, then show you some equations and talk about some more illustrative examples, and include some takeaways for how this could inform what we do here at Tools Group. So let's start with this guy. This is Judea Pearl. Judea Pearl laid back in the 80s a lot of the foundation for modern artificial intelligence. He pioneered Bayesian networks and probabilistic AIs. And for this work in 2011, he got a Turing Award. And for the last 40 years or so, he's been trying to push this philosophy, mathematics, and notational system of what he calls do calculus. That said, Judea is just kind of an ass. He regularly does things like refer to all of machine learning as glorified curve fitting. He shows up to conventions and tells everyone else that they're doing everything wrong and need to do things his way. He's just a very confrontational guy. He's also just a terrible writer. I cannot convey enough how just god-awful he is at conveying his ideas. And because of those two facts, for a long time, people have just been ignoring him. He's really been publishing into a void since the 80s, up until about 10 years ago, when there's been a much bigger explosion in research on the stuff he's been talking about, because it turns out that, perhaps unfortunately, he is probably right about this stuff.
So they caught up to him.
Yeah. So what is this stuff? This stuff is causal inference. Causal inference is the process of determining the independent actual effects of a particular phenomenon that's a component of a larger system. This is a branch of statistics, specifically Bayesian statistics, which means that we are concerned with finding probability distributions which incorporate prior knowledge. In addition to this prior knowledge, causal inference induces a concept called causal graphs, where this prior knowledge is used to construct hierarchical relationships between variables. So to give a quick example of this, in this example, we are interested in perhaps the recovery time from an illness. How quickly somebody recovers depends on how severe the illness was, and also whether they take medication. And in addition, whether or not somebody takes medication often will depend on the severity of illness as well, which leaves us with this little triangle here where these arrows indicate the direction of causality. I don't want to spend too much time on this, but the slide's here if anyone wants to look over it later. But just to give a couple of quick definitions, by variable, I'm talking about any property or descriptor that can take multiple values. I'm going to annotate these with capital letters. So for example, in a medication study, capital A might refer to the age of participants. An event is a specific measurement of that variable. So for participant 1, capital A might be 15, which I will indicate with a lowercase. And the other thing about variables is every node on these causal diagrams is a variable. When they are assigned values, that is an event. The other thing I want to talk about quickly is Bayesian notation, for those of you who are perhaps familiar with this. You'll often see equations that look like this guy right here. This is showing the probability distribution, so something like a bell curve or just a straight percentage, of variable y conditioned on our knowledge x. This is the Bayesian framework, which is different from the frequentist framework of statistics. But in general, this is different from the joint distribution, which is the probability of y and x both occurring. Again, there's a little example here that you can look over later, but that's just what this little line here means. It's the conditional. So we say, we know x happened. What does that mean about y? So with that in mind, I want to go on to just getting back to causal inference. Primarily what we're interested in with causal inference is what happens when we make an intervention to a system, which in the language of causal inference we call performing a do. So here we have a more complicated causal diagram. Let's say we're interested in the effects of X on variable Y. So we might imagine that X is sales promotion and Y is total sales. Both whether something gets put on sale and what those actual total sales are themselves the results of multiple causes. And we might map them out something like this. But the important point here is like historically, when a 10% discount was applied, it was applied because of reasons. And because it was applied for reasons, a simple correlation between the 10% discounts and the effect on sales is not sufficient. With a correlation, we're going to pick up confounding effects from all of these other variables. So we could ask, for example, what effect promotion X equals X naught has on sales. We're talking about arbitrarily assigning a value to X. This results in mutating a diagram, which gives us something like this, where we have broken the incoming causal links to X, and we're now just arbitrarily assigning a value of X naught. This has ramifications to statistics that have to be carefully considered. But again, the important point is that in general, the effect of the distribution of Y conditioned on X naught occurring is different from the distribution of Y when we make X naught occur. And don't worry, I will be explaining this all in detail in the rest of this presentation. So for my first example, let's say I have an espresso machine. My espresso machine has an internal pressure Y, which is reported by a barometer X. So one question I could ask is, what is the probability distribution of Y? Well, it's probably going to look something like this, where normally my machine is turned off, so there's a big spike at 0. Sometimes I turn it on, which is this long flat line. And when I do leave it on, I tend to leave it on for a long time, so there's a little bit of a spike there, it's maximum pressure as well. We could also ask, what is the probability distribution of Y conditioned on X equals free? And this presumably will look something like this. It'll be some kind of bell curve centered on Y equals free, because presumably my barometer is accurate, and its width there will be the accuracy of my barometer. Another thing we'd ask is, what is the probability distribution of Y conditioned on doing X equals free? We're here, instead of just saying when X equals free, we're saying we make an intervention making X equals free. Does anyone have a thought on what this will look like?
Earlier, you said Y equals 3, and I think you meant X equals 3 when you're talking about the middle graph.
No. When X equals free, Y is also equal to free.
Oh, yes, when they're both equal.
Yes.
Showing, yeah. I see what you mean. Okay.
But anyway, getting to this is do. The answer is it's probably going to look like this. It's going to be the same as the probability distribution of Y normally. The reason for this is that what I've done here is I have broken my barometer. When I say do X equals free, I have smashed the glass, I have taken a piece of tape, and I have taped the arrow down to point at free, and I have said, what effect does this have on the pressure? And the answer is it has no effect. Obviously, taping down the arrow to point at free has no effect on pressure. Since the barometer does not cause pressure, it simply reports it. And this is again seen by those mutated causal graphs, where instead of the pressure informing the barometer, now we simply have the barometer telling you a value of free, irregardless of the pressure. To give another example, we have Bergson's paradox. This is a classical example that we've shown in most introductory statistics courses. So to talk about Bergson's paradox, let's say, let's make a model of my dating tendencies. So when I consider dating a woman, I assign to them their attractiveness A and their niceness N. And from these two causals, I'll derive their dateability D. For the sake of simplicity, let's say that A and N are both random numbers from 1 to 100. And my dateability, well, I'm a simple guy. I just do A plus N greater than 125. So now we can take this and map out the space of all women where we have their attractiveness and niceness. And as I said, these are uncorrelated random variables. So we're going to end up with a flat distribution. Onto this flat distribution, I can project my dateability lines up in there. And we're going to end up with the group that I will date and the group that I will not date. And we end up with these two groups. The point I want to make here is that by conditioning on D and only looking at a subset of the women I'm interested in dating, I've now induced a correlation between attractiveness and niceness. This is perhaps more obvious if we modify the equation and we say instead of just greater than 125, it's less than 150 as well, where now we have a second line, which is the women I don't date because they date better men than me. But again, we now just want to look at this sample set of the women I'm dating, and we'll see that there's a clear negative correlation between niceness and attractiveness. So I might say something like, hey, has anyone ever noticed how women are, less nice as they get more attractive? No, that is not a true statement. That is just an observation because that's not a feature of the full population. That's just a condition that's happened, a correlation that's arisen because I've conditioned on D. This is probably the most common cause of sampling bias, and this happens all the time. And the reason this is happening is because D here is what we call a collider node. It is a variable that is informed by two separate, unrelated other variables. They both have arrows pointing inward, so it is a collider. And when you condition on colliders, you induce correlations that otherwise are not present in the data. To give a perhaps more serious example, let's look at another medical study. We are interested in whether a patient takes a pill and the effect it has on a patient's recovery time. We might also know that patient's recovery time depends on the severity of the disease. And for a variety of economic or social reasons, whether or not somebody takes a pill could be impacted by their ethnicity. But in addition to these effects, we also are going to be conditioning on whether we actually see these results or not for each patient. And whether somebody reports the results is probably going to be conditioned on the severity of the disease. For example, somebody who's only very lightly sick might not even notice, and they wouldn't seem to report it. And also, I don't know how much you guys know about the history of medical experimentation in the United States and elsewhere, but for a, let's say, wide assortment of incredibly valid reasons, certain populations are a little hesitant about engaging with the medical establishment. So whether or not somebody reports also probably depends on their ethnicity. What this means is that when we look at the actual data we have, which is only data that has been reported, there is now a correlation between ethnicity and severity of disease that is not a feature of the general population. Furthermore, this correlation is going to have an impact on the effect that we're looking at, which is the effect of taking a pill on recovery. Normally, whether somebody takes a pill or not, the effect it has on recovery is not correlated to ethnicity, but because of this conditioning, it will be. This is hugely important, and it happens basically all of the time in every attempt at science that's ever been made, because it's just so hard to deal with. In addition to it just arising naturally because of features like whether people report things, very often in experimental studies, experimenters will try to control for as many variables as possible. And what that means is that by controlling for the variables you can control for, you often will induce correlations in the variables you can't control for, things that you might not even be noticing, like weather or mood or other conditions people have. All these things are not correlated in the general population, but once you start conditioning on some of your variables, they will become correlated. The reason this happens is because of what Pearl calls backdoor paths. In addition to the front door cause of X on Y, there's also this backdoor path of confounding variables. Because of these backdoor paths in general, the probability distribution of Y conditioned on doing an intervention is not the same as the probability of Y if that effect X had occurred naturally within the system. Pearl provides in his work a list of rules to follow to ensure that all of these backdoor paths are closed. And in essence, this amounts to controlling for certain variables. But in order to do that, we need to be able to accurately make these causal diagrams. We have to accurately be able to map out all of the causals and the effects that they have on one another so that we can see where these backdoor paths are and what we need to do to close them off. Let's look at another classic example to see backdoor paths and not action. Simpson's paradox is a well-known phenomenon where a statistical association that holds for an entire population is reversed in every subpopulation. So for example, say we have another medical study where here we have some patients who took a drug, some who did not, and we recorded whether or not they recovered. The top set of data here is showing the whole study. These bottom two are the same data, just broken apart by gender. So these numbers will add up, like 18 and 2 add up to this 20 here. What we can see is that in the population at large, 50% of the patients given a drug recovered, but only 40% of the patients who were not given a drug recovered, which seems to indicate that this drug is effective. However, when the data is broken apart by gender, we can see that for both men and women independently, the phenomenon is reversed. Recovery rates are lower in the groups that took the medication than they are in the groups that did not take the medication. How can this be? The answer is that there are asymmetries in the data. Both men are more likely to take the drug. As we saw here, 30 of the 40 men took the drug, but only 10 of the 40 women took the drug. And men are more likely to recover regardless of whether or not they take the drug. Because of this, the combined group contains a large number of men who recovered perhaps despite taking the drug. So a researcher is left with the question, which should you recommend this drug or not? I'll again open it up if any audience has any insight into that. Would you recommend this drug? Anyone?
No.
No? All right. So yeah, a naive answer might be that for men, you look at this data, don't recommend it. For women, you look at this data, don't recommend it. But for a patient whose gender you don't know, you'd look up here and say, oh yeah, you should take it, which is obviously nonsensical, right? Once we introduce causal diagrams, this situation becomes a lot more clear. We can assume, based on our prior knowledge, that this pill is not causing gender, right? But we clearly see an effect on whether or not the pill is taken. We clearly see a correlation between whether or not you take the pill and gender. So from that, we can probably infer that gender has a causal link to whether or not the patient takes the pill. This means that gender here has become a backdoor path, as we were talking about before. So we need to control for gender as a parameter, which probably means that this drug is not good. We should be looking at these split data. But we could also ask, what if instead of measuring gender, F was a measure of blood pressure? Well, in this case, it's quite plausible that whether or not you take this pill has an effect on blood pressure. And that arrow is now going to look in this direction. F is no longer a backdoor path here. It's now a front door path. The effect that blood pressure has on a patient's result is in part related to whether or not they took the pill. So now we would want to include this effect. We would not want to control for F. And we would end up with the conclusion that we should look at this top set of data and that the drug is in fact good. The important point I want to make here is that both of these causal graphs are completely consistent with this data. Just by looking at this data, we actually could not say whether or not the drug was good. We need to have an understanding of the causal structure. We need our prior knowledge that treatment does not cause gender in order to correctly interpret the data we have. This is going to be a recurring problem with causal inference, that these causal graphs are just not, you can't create them just by looking at data. This is just another example of Simpson's paradox I want to put up here for a moment because I think it really clearly shows what's happening. You can see that for this data set as a whole, it looks like there is a positive correlation between exercise and cholesterol. However, once we break it apart by age groups, we can see that for every single age group, there is actually a negative correlation between exercise and cholesterol. The reason this happens is, again, because age is a causal for both cholesterol and exercise independently. So when we plot the data as a whole, Simpson's paradox can occur, and we'll get this anomaly. I'm not going to spend too much time on this because this is just the math part, but by doing his calculus, Pearl arrives at this equation here, where in this equation, T is a set of variables that will close all backdoor paths. And the important part is that on the right-hand side, we've eliminated all of these do's, and we've reduced the equation to traditional classical statistical quantities of conditional probabilities. In the case of this graph we've looked at a couple of times now, where with these free z's, Pearl is able to show that z1 and z3 together make one of these sets that close off all backdoors. Just z3 by itself, even though it looks like it blocks all those arrows, is not sufficient to close off the backdoors, because as we saw, conditioning on z3 introduces a correlation between z1 and z2. So in order to accurately do this, we need to condition on both z1 and z3, and we end up with this equation here, which is just basically what it means to control for a variable in the mathematics of do calculus. So applying this to Simpson's paradox again, what we are interested in is the effect of a policy either prescribing taking a drug or prescribing not taking a drug. So as we saw, originally we have a causal diagram like this, where whether or not a patient takes the medication is informed in part by their gender. But what we're thinking about doing is just breaking that causal link. applying an interventional do and just saying everyone should take this drug or everyone should not take this drug. So working out the math, we use that equation from the last slide. We say the probability of recovery, if we condition this on doing take the drug, an intervention, is the probability of recovery conditioned on people in our study who took the drug are male times the probability of male, plus the probability conditioned on taking the drug and being female times the probability of female, which came out 0.4. And same thing for probability of recovery if we do not take the drug, just replacing taking drug with not taking the drug. This comes out to 0.5. So we can conclude that the probability of recovery, if we say everyone takes a drug, minus the probability of recovery where nobody takes a drug, is negative 0.1. Thus, the drug is bad. We do not want to prescribe this drug to anyone. This is, again, different from the conditional probability of recovery conditioned on taking a drug minus conditioned on not taking a drug, which is just a difference between these two percentages, as we saw earlier, which is positive 0.01. The fact that these two numbers are mirrored is just a coincidence. Don't read too much into that. But the real important take home here is that we had an observational study. This is not a controlled random experiment where the scientist was saying, you take it, you don't take it. This was an observational study of how people chose to use this drug in just normal course of actions. We did not need to do an actual, probably very expensive controlled experiment to derive this result. Just with our prior knowledge that treatment does not cause gender and an observational study, we can derive a conclusion about whether or not this drug should be used. This is another example I want to go over, I picked up from a blog. These three equations are all statistical probability distributions, and they all produce the same distribution. It should be immediately obvious from substitution that blue and red are the same. You can just plug in rand n for x or for z. You can trust me that green also produces the same distribution, or we can just take some samplings of it. So here we have sampled all three of these distributions. In addition to the samplings, we plotted the probability distribution of x and the probability distribution of y along the axes. And you can see from the statistical analyses that these are all producing the same distribution. However, despite producing the same distribution, they have different causal diagrams, and I'll come back to that in a second. But first, I again want to highlight this point. The mapping from causal diagrams to joint distributions is many to one. Several causal diagrams are compatible with the same joint distribution, so generally it's impossible to determine your causal relationships just by looking at your observed data. But to go on with this experiment, what I'm going to do now is perform an intervention. Specifically, I'm going to make x equals to 3. I do this by just putting the line x equals 3 there between each other line. And now we get these distributions, where we're now looking at the probability distribution of y and x conditioned on doing x equals 3. So unsurprisingly, all three distributions, x is going to be equal to 3 because we've set it that way. But the interesting thing is that the y distributions are no longer identical. They were previously, but once we do this intervention, they are not. This is easy to see in the plots, where here we have plotted the probability distribution of y conditioned on doing x equals 3. And here we've plotted the probability distribution of y when x equals 3. And again, causal diagrams are going to tell us why this is occurring. In the case of blue, x causes y. So we have this diagram here. There are no backdoor paths. And we apply this do operation. We're not changing anything. So the probability distribution of y conditioned on doing x is the same as the probability distribution of y conditioned on x just happening because of this causal diagram. In the case of green, we have something like the espresso machine example, where y is causing x. And we can see now that by applying this do, we are breaking that causal link, just like in the espresso example. And so now the probability distribution of y conditioned on doing x is the same as just the probability distribution of y originally. In the case of red, we are introducing a third variable, which has a causal effect on both x and y. And so when we perform this do operation, we are again breaking the incoming links to x, which has no effect on y because x does not inform y in any way. So when we do probability of y conditioned on do x, that's also going to be the same as the probability distribution of y naturally. We can arrive at this conclusion by doing Pearl's calculus, the same way we did for Simpson's paradox. And we get the graph here on the left, where we've used causal inference and that equation to estimate the effect of py do x equals 3. And on the right, we have just a simulated intervention by running these equations, and we see that we get the same results. To give another example, perhaps a more practical one, this is from Lyft, where they were interested in the effect they have their coupon budget on their rides and their actual income. So they came up with this causal diagram. And from this, so they did like taking how many people want rides coupled with the weather combines into how many actual people log into their app. Based on people who log into their app, how many drivers are available, and the budget for coupons, they get a price. Based on this price, drivers and weather to get a conversion. Based on people who are on the app and these conversions they have to get rides actually happen. And I assume they probably also based on price and rides, we could have a revenue box over here. And from this diagram, and by doing the causal mathematics, they were able to derive some actionable insights into how their coupon budget affects their revenue and their rides. One important thing to note here is that many of these nodes, they have actual direct statistics for it. They know how many sessions they have. They know how many driver hours they have. They know what the prices are. All of these things are handled internally by their own software, so they have actual metrics. And in fact, some of them, like price, are calculated in their software. So not only do they have metrics, they also know exactly which factors feed into it, so they're able to accurately draw this causal diagram. That said, I would question this diagram. For example, I think that coupon budget probably has an effect on how many people want to take rides in the first place. That's kind of the point that it advertises. But regardless, this is what they did, and these are the insights that they drew from this that they were willing to share publicly. But the main point I want to make here is that when you're looking at something that is a code base that you yourself have written, you can draw a very accurate causal diagram because it's code. You know what the inputs are, and you know what the outputs are, and you even know the equations that relate to those things. For this example, I tried to create something similar using a similar causal diagram for promotion sensitivity. I came up with this. This is obviously super incomplete, and it already shows that there's a very large number of variables that we just have no way of measuring. For this reason, at this time, I'm uncertain whether we'll be able to use do calculus to help us designing products like this, especially since do calculus has to be compared against the immense power of our correlative modeling systems, such as LightGBM, that are able to look at broad swaths of data and do a very complex correlative analysis of these relations. That said, I do want to highlight one very important point, which I've come back to several times now, which is that the data in our database is not a pure random experiment. The decisions that were made in the past, such as what discounts to do, were themselves made based on other factors that are probably included in our data as well. For this reason, performing an intervention, like arbitrarily assigning a 10% discount, is not the same as that 10% discount arising naturally through the system. We cannot simply search for a correlative link as we do with our machine learning algorithms. That's inherently risky because we are likely to misattribute as correlative effects something that's actually caused by hidden confounding variables. Before concluding, I want to make one more brief, quick note about counterfactuals. I would say, in addition to interventions, counterfactuals are probably the other big thrust of Perl's work. A counterfactual is a if hypothetical statement where the contents of that if are unobserved. So the fully general one would be something like find the probability that if x had been x prime, y would have been a y prime, given that in reality x was x and y was y. For example, this could be find the probability that if promotions had been 10%, sales would have been 150, given that in reality, the promotion was 0 and sales were 120. Or to give another example, let's say you hit me with a car, event x equals x, and afterwards I needed surgery, event y equals y. Your lawyer is going to argue that if I had not been hit by a car, if x had been x prime, I would still have needed the surgery anyway, y would still be y, and thus it's not his client's responsibility. My lawyer is, of course, going to claim that if I had not been hit by a car, if x had been x prime, I would not have needed the surgery, y would be y prime, and thus it's your responsibility to pay for it. Mathematically, this is what we call the probability of necessity, which is given by this equation here. The probability of necessity of x and y is a probability that y in a universe where x equaled x prime would have been y prime, given the actual data that x was x and y was y. In his work, Pearl was able to derive that this equation can be expressed with this equation here, where this first term is what we call the excess risk ratio. This would be using the example above, the probability that someone needs surgery after being hit by a car minus the probability of needing surgery if you're not hit by a car. So say, for example, if 10% of people who are hit by cars need surgery and only 1% of people who aren't hit by cars need surgery, this would be 10% minus 1% is 9%, divided by 10% is going to be 90%. So the excess risk of you hitting with that car caused me a 90% increase in the odds that I would need surgery. Traditionally, this first term has been the only one considered. If you went to a court, especially a court from maybe 5 or 10 years ago before this sort of research was used widely, that's probably the only number that the expert witness would bring up. The difference in risk because the thing had occurred minus the risk had that thing not occurred divided by that factor. What Pearl shows is that there is actually a second effect, the confounding factor, which needs to be considered. This arises from those backdoor effects. So, for example, it might be the case that people who get hit by cars tend to be people who lead riskier lives and just otherwise engage in risky behavior, and thus are more likely to need surgery in general than the general population. Or it could be the case that people who get hit by cars tend to be more sedentary and thus are more prone to injury. Any of these things could be the case. It could be any number of factors, but by just looking at excess risk ratio, we're leaving off this confounding bias that might also be occurring. You can note that in a case that there are no backdoor paths, if there are no confounding variables, then py condition on x prime is equal to py condition on doing x prime, and this term goes away. It's also very interesting to note that with both observational and experimental data, all 6 of these terms of this equation can be found without invoking due calculus or requiring causal diagrams. So in cases that have both observational and experimental studies, which, for example, hitting people with cars might be, though I don't know if anyone's ever done an experiment with that, you can basically solve this equation without having to do any more complex math, just by plugging in the numbers that you can get straight from the data. So coming around on my takeaways from this, due calculus requires some extensive knowledge of the causal framework and all of those connections between causes. We have to be able to identify what the backdoor effects are and where they're occurring in order to do this. In order to accurately control for these confounding effects, we also need to be able to measure many of these intermediary variables. We need to have values for them so we can come up with their probability distributions so we can multiply them into Pearl's equation. The main point that I really have been harping on many times here, though, is we have to be careful with our data selection. The prescriptions we're analyzing, again, things like whether or not an item is put on promotion, is itself historically selected for reasons that are caused by the data. And just looking again at that correlative link between promotions and sales, we're leaving out these confounding effects that need to be accounted for. One thing to note, though, is that at least in the domain of forecasting, we're concerned with causals, but we're not forcing them. We're not performing interventions. We're saying, given these causals, what is the effect going to be? Which means that we actually do want those backdoor paths open. So for forecasting, we don't need to worry about this. We can just correlate everything because we're not talking about doing interventions. Where due calculus will be applicable will be to intervention problems. This would be things like price optimization, promotion optimization, assortment planning on the tools group side, S&OP, all the places we're saying, what is the effect of this thing going to be? We're looking at counterfactuals. What would happen if we put a 10% discount up there? And that's where this due calculus stuff is going to be relevant. Another very important point is that any hypothesis we make from this will be fundamentally untestable. That is a consequence of counterfactuals. I cannot say would I need surgery if I was hit by a car versus would I need surgery if I wasn't hit by a car, because I can't both be hit by a car and not hit by a car, right? Only one set of things can happen. So any hypotheses we make, we can't actually test, which is a huge problem for data scientists like me. And one other thing, like I mentioned earlier, there is definitely truth that comes out of this due calculus. We actually draw the meaningful causal relationships rather than just looking at correlative effects. But we will lose a lot of the system-wide advantage of the complex machine learning algorithms because we are just looking at probability distributions rather than, because this is a statistical framework, we are looking at just each individual case taken on its own as a subset of the whole. Whereas those machine learning cases, they learn from every single example in the database in order to compound all those effects into one framework. These are just some references I use for this. If you're interested in reading more about this topic, I would highly recommend starting with this blog. That's where the red, green, and blue example came from. It does a really good job of explaining it very, very succinctly. If you're more interested in that, this book is extremely good. I regret that it was the last part that I read because it was way better than all those other papers and really did a great job of explaining how all this occurs. But yeah, that is everything I got. So thank you for listening. Are there any questions? All right. Well, thanks for coming, everyone. I'm curious whether you guys got anything out of this. I hope the data science team really gets more out of this, perhaps. But very interesting stuff for me, at least. I really enjoyed learning all these things.
That was awesome. Thank you.
Yeah, it is awesome.
Yeah,
Thank you.
Thank you.
Very interesting indeed.
Yeah, I actually followed along pretty well there. I enjoyed that greatly, especially about who you would date and who you wouldn't.
It actually is like the first example of the Bergson paradox on like Wikipedia is the same dating thing. Simply because it comes up all the time, right? People say things like that, and the answer is no. That's not a thing you've observed. That's just your sampling. You just look at a subset and draw a conclusion.
So I get where you said, forecasting, we're going to keep, all the causality in place, and in the other, the other examples where this could be used, I follow that as well. But sorry, I couldn't tell from like the graph where you put all of the different pricing, causality, and the real life type of thing. Did you say that like we can't really break that down well enough?
Yeah, so this was my attempt at just quickly, I have spent more than quickly on this, to come up with an actual framework that would relate the discount to the sales. And what I found is that in trying to do that, I had to basically start introducing a lot of things I don't know, like population traits, product traits, the availability of similar products at other stores. Like we're not going to have a metric for that. And all of these things have a role, right, on sales. And so if we're just looking at backdoor paths between, say, the next week's discount and next week's sales, well, we see one through the cost to produce the item and product availability. We see ones through historical sales and product availability. We see ones through this, what I've called local product goodness, which is basically how desirable this thing is, which is not a thing we can directly measure because what we measure is historical sales, which will depend on this local goodness as well as on the availability of product elsewhere. So in the Lyft example, they know how many sessions they have. They know what prices they offer. They know how many driver hours are available because all of these things are handled internally on their app itself, and they can just drive a metric. In this promotion example, I very quickly realized that there's just a ton of things that we can't get a number for. And it's possible. So one of my personal big takeaways, because I know I'm going to look at promotion sensitivity eventually, is that price is sitting here as a confounding variable for a lot of things, however I slice it up. So controlling for price might actually be a really good idea. It might also just be a bad idea because of that Bergson paradox I talked about. I need to look into it a little more carefully. But price would just be like, for example, when considering the effect of a 10% discount, it might be very wise to break it apart by what effect does 10% discount have on a cheap item versus what percent does 10% discount have on an expensive item. Which is one takeaway for me, at least, that I'm going to keep in mind when I go forward with a product promotion optimization at some point. But yeah, doing the full do calculus stuff would require being able to close every backdoor path, which would require A, identifying every backdoor path, and B, having statistics for a sufficient subset of those variables to actually be able to perform Pearl's equations. And again, I'm stacking this up against the just straight up raw power of, say, like GBM to compute a very strong correlative effect between these two things, which might be biased because of all these inherent confounding biases, but still is going to be a very powerful correlative effect that we definitely can sell as the prediction.
Yeah, so I mean, with life being what life is, right? There's so many backdoor paths to everything. You know what?
Yeah.
You
Yeah.
can't. What drove a purchasing decision, and but the buyer's ethnicity, etc., the weather, all this stuff. You can't isolate everything from there. So. Are you saying maybe there's some pieces with price or whatever? Like, can we use this going forward? Like, or is this like, hey, this makes a lot of sense mathematically, but like, there's just no way to isolate enough data to use this?
So, two points. First of all, like I said, highlighting that price is going to be on those backdoor paths for a lot of the other routes has itself just informed me that I should be controlling for price when I look at promotions, unless it's going to be a collider node, which it looked like it wasn't because it's directly informing those things. So that already is a takeaway for me, is that like controlling for price and promotion sensitivity is probably important, and that's the kind of thing that I'll test when I start doing tests on these. Like I also said, it's hard to test. I can't test an intervention on the database because all of the information I have on the database is observational. I can't say what would have happened for this particular product had it been on discount. So it is likely that I'm not going to be able to use this stuff directly. I kind of doubt that I'm going to be using Pro's equation itself, but I certainly will be drawing causal diagrams, and I certainly will be looking for nodes like price that are sitting on a lot of the backdoor paths that might be useful to close off. The other point I want to make, this is another example I didn't end up using in the presentation, but this is by a company like Google or something that is looking at advertisements. And for this one, the inputs are basically the list of ads they have available and the intent of a user. But every other node here is part of their software. Their software takes the query and the inventory and selects a list of ads. Their software takes the query and the ads and scores them all. Their software takes the scores and the ads and the bids and makes a slate of ads for them, the user. Because these are all handled internally by their software, they know what the inputs are and they know where it's used elsewhere. So this causal diagram is perfect because these are all pieces of software that take things as input. So they just need to like draw the arrows for where things are used as input to other functions. What this means is that they could do calculators probably very precisely if they wanted to, say, control for scores by adding 10 to every, I don't know, ad that's directed for alcohol or something. They could, without doing an experimental study, they could derive the effect that would have just by the observational data and this do calculus. There are probably parts of our software where that might be useful. Certainly in the more complex things, like if you look at allocations or replenishment as a whole, there might be ways that we can use that. So that's also just a thing to keep in mind.
Yeah, when you think about like what we have internally, I'm thinking about this in the area of like attributes and AP, which I know we talked about, with you over the last few weeks of, if looking at attribute history and, does blue sell better than green? What about blue cotton? What about, this, that, or the other? The more of these attributes that you have and treating them as, causal backdoors or whatever, I think that's really an interesting way to think about this. So maybe we can, use whatever data points we actually have in a framework such as this, but we're obviously not going to control for everything. But no, this is a good way to think about things. So I appreciate it.
And yeah, it's a little unfortunate I've already concluded the SHAP value research, because the SHAP values are basically the strongest way to look at the correlative effects. But they will definitely lose out on direct causal effects because they don't incorporate this prior knowledge. And as we saw, if we don't incorporate the prior knowledge to make these causal diagrams, we can only look at correlation. We can't look at causality. Oh, awesome. Any other questions?
No, thanks again.
All right. Well, thank you so much.
No,
now
thanks.
we'll stop recording. Thanks, guys.
Thank you. See ya.